Okay, thank you for the introduction. Hi, I'm Seungmin Jeon from KAIST. Today I will introduce our work on novel quantum approach for analyzing probabilistic systems. Let's start by understanding probabilistic systems. Probabilistic systems are designed to handle real-world uncertainty using probabilistic behavior. For instance, distributed systems, autonomous driving, and weather forecasting include probabilistic behavior to handle uncertainty in our reality. These probabilistic systems must be carefully analyzed before use because errors can cause significant damage in our daily life. To prevent such errors, probabilistic model checking is a great tool for analyzing probabilistic systems. It typically involves 3 steps. First, describing the probabilistic model, including states and transitions, like 50% probability of staying sunny or transitioning to rainy. Second, specifying the property to analyze, such as what is the probability of reaching a sunny state after 2 days. Then the model checker computes the result by extracting the transition matrix, performing matrix multiplication, and calculating the probability of reaching target state. This tool is robust and user-friendly as it automatically explores all possible states and performs the calculations. However, verifying large systems with high accuracy is challenging. Large systems are typically described by defining multiple variables. As the number of variables grows, the number of states increases exponentially. For n variables, each with 2 states, the total states become 2 to n. Therefore, numerical approaches require large computations because of the state explosion problem. The state explosion problem can be avoided by a statistical approach, but it requires significantly more samples than the desired accuracy. For example, to achieve 10 times higher accuracy, we need 100 times more samples. This is known as the runtime explosion problem. So there is a trade-off between scalability and accuracy. Numerical approaches provide high accuracy but do not scale well because of the state explosion. Statistical approaches are scalable but hard to achieve high accuracy because of the runtime explosion. To bridge this gap, you can leverage a quantum computer. But how quantum computer can achieve both criteria at the same time? Our key insight is that the computations required for the model checking can be performed more efficiently on a quantum computer. For scalability, we address the state explosion problem using quantum superposition, which is a key feature of quantum computer. For accuracy, we address the runtime explosion problem using quantum amplitude estimation, which is an efficient quantum algorithm to get useful information from a quantum state. By combining these techniques, you can analyze large probabilistic systems with high accuracy much faster than classical computers. Let's start by understanding how quantum computer resolve the state explosion problem. In quantum computer, a qubit is a unit of information like a classical bit, but it can exist in a superposition of 0 and 1, which is a key difference from classical bit. This superposition allows a qubit to be interpreted as a probability distribution over 2 states. For instance, a 2-state probability distribution on the left can be represented by 1 qubit with a 30% probability of being sunny state and 70% probability of being rainy state. Similarly, n qubits represent a 2 to n state probability distribution. For example, an 8-state probability distribution can be represented in 3 qubits, where each state has its own probability, such as 50% for sunny state, and so on. This superposition allows us to address state explosion by representing large probability distribution and its transitions with exponentially fewer resources. Because n qubits represent 2 to n states, modifying n qubit is equivalent to modifying 2 to n state probability distribution. For example, modifying 3 qubits is the same as modifying 8-state probability distribution. This allows large matrix computations to be represented with exponentially fewer resources. For instance, a matrix multiplication of size 2 to n can be represented with only O(n) qubit systems. Next, the runtime explosion problem is resolved by the quantum amplitude estimation algorithm. For example, consider a property that asks for the probability of being sunny state after 2 days. By encoding weather state and their transitions as qubit and quantum operations, respectively, you can replicate the probability distribution after 2 days. But even if you have this quantum state, you cannot directly access the information. It's actually hidden, so we need a special method to extract classical information from a quantum state. QAE is an advanced quantum algorithm that provides the probability information of interest. It estimates the probability by using multiple quantum samples, where each sample represents a construction of the probability distribution as shown on the left. This process allows us to estimate the probability of a sunny state, which is close to 75%. By using QAE, we can address the runtime exclusion problem as it requires a linear increase in the number of samples with accuracy. To leverage these techniques, we need to implement a quantum operation as a quantum circuit, which is the actual model for quantum computation. The key component is the state transition circuit as shown on the right. In this circuit model, qubits are represented as wires, and quantum gates are represented as load on these wires. The horizontal axis represents the flow of time. Here, the first and second lays are encoded in the upper and lower qubits, respectively. The quantum gate applied to these two qubits replicate the state transition by taking the first state qubit as input and the second state qubit as output. Formally, these gates produce the next state for given the current state. Our quantum approach works by repeatedly using the state transition circuit. The overall workflow is as follows. First, given the model, we construct the transition circuit by translating model into quantum circuit. Next, given the property, we construct the model checking circuit by translating property into quantum circuit. For example, if the property asks for the probability of being sunny state after 2 days, we first encode the initial state and repeat the transition circuit twice. Then we encode the result, probability that sunny on day 2 is true, into the bottom result qubit. The final step is to extract the probability that the result qubit is in the true state. This is achieved using the QA algorithm as mentioned earlier. The main challenge in this workflow is translating the model into a state transition circuit. The other steps are relatively trivial, involving the repetition of the transition circuit and the use of the well-known QA algorithm. So I will show that how to translate the model into a quantum circuit. Here is an overview of how we translate the model. To build a transition circuit, we translate the model in 3 parts. For example, the weather model on the left is divided into 3 functions: guard, choice, and update. These functions are translated into corresponding circuits as shown on the right. The guard circuit for evaluating the guard condition, the choice circuit for preparing the possible choices, and the update circuit for evaluating the update to calculate the next state. Together, they form the state transition circuit for the model, which produces the next state S prime given the current state S. Now let's explore each part in detail. First, the guard function calculates the guard conditions. For example, if the current state S is 0, the flag for the first command G1 is set to 1. If S is 1, the flag for the second command G2 is set to 1. These calculations are replicated by controlled X gate shown on the right. The left gate in a box replicates the calculation of first guard by applying the X gate to the Jeon qubit controlled by the state qubit S. The controlled gate is similar to a classical if statement, and the X gate is similar to a classical NOT gate. In this way, classical logics can be replicated using quantum versions of classical gate. Next, the choice function prepares probabilistic choices for each command. In the weather model, the first and second commands have 50-50% probabilistic choices and 100% single choice, respectively. These choices are created using a rotation gate as shown on the right. The first gate in a box is control rotation gate to prepare the choices of the first command. It modifies the choice qubit, CH, to encode a 50-50 probability when the first guard is 1. The second gate is control identity gate for second command, but it essentially doesn't need to do anything, as the choice qubit initially represents a 100% probability of being 0. By adjusting the rotation angle of the gate, we can replicate any probability distribution on the choice qubit. Finally, the update function calculates the next state based on the selected command and probability choice. In the model, 2 updates of first command update the next state to 0 and 1, respectively. These updates are implemented using controlled identity or X gate, where the controller selects the command and choice, and the identity or X gate sets the next state. The update circuit can be constructed like the guard circuit because it needs to translate classical logic into quantum gate. Similarly, you can translate more complex model into a transition circuit in the same way. For example, on the left, we can see a model with more complex expression and probabilities. The model is still broken down into guard, choice, and update functions, where the guard, choice, and updates can be any Boolean expression, any probability distribution, and any assignment expression, respectively. These functions are then translated into their respective circuits, the guard circuit, the choice circuit, and the update circuit, as shown on the right. As we saw earlier, each circuit performs the role of each corresponding function, forming the state transition circuit that produces the next state S prime and D prime, given the current state S and D. In summary, we can translate the model into a transition circuit using a three-step translation. Then by repeating the transition circuit and utilizing QA algorithm, you can perform probabilistic model checking on a quantum computer. We analyzed our algorithm for the translation time on a classical computer, the execution time on a quantum computer, and the resource requirement. Translation time is another major concern as we directly translate the high-level input into quantum circuits. Because the size of the input is manageable, the translation process is not a bottleneck in the end-to-end process. In the next slide, I will explain the time complexity and resource requirements. First, we compare the time complexity of the classical and quantum approaches. We focus on comparing the statistical method because both are scalable and provide probabilistic answer with accuracy improving over time. For the analysis, you assume M is the model, T is the number of transitions, epsilon is the error bound. The result shows that our quantum approach is quadratically faster for the same accuracy. This comes from two factors. First, the single sampling cost is the same as in the classical approach because our translation keeps it proportional to the number of operations in the model. And second, QA achieves the same accuracy with quadratically fewer samples. This speed-up is particularly beneficial for analyzing critical systems, which requires extremely small error bounds to prevent rare events. Next, we analyze the resource requirements of our quantum approach. To do this, we implemented our translation method in Qiskit and counted the number of qubits and KAIST in the translated circuit. We used case study from a benchmark shoot with state space and transitions ranging from 2 to 24 to 101 and 4 to 100 respectively. As a result, we found that the required qubits range from 1,000 to over 10,000, and the number of gates ranging from 100K to over 1,000K. While these requirements are not feasible with current quantum hardware, we are hopeful it will be available soon as companies like IBM and Google aim to build practical quantum computers in the near future. So far, I have explained how to use a quantum computer to perform probabilistic model checking. The paper includes additional details not covered in this talk, such as translation details, qubit optimizations, and quality proofs. Please refer to the paper for more detail. Thank you for your attention.
Question session? Thank you for the very nice talk. Given that amplitude estimation offers a quadratic speed up, whereas the runtime blow up of model checking is exponential, could you give an idea of the largest concrete problem sizes that become tractable under the quantum approach?
Could you please explain again what the exponential complexity comes from?
You showed earlier on the runtime slides, right, that the
Yeah.
not on this slide, but earlier on in the talk when you first introduced the complexity of model checking.
Complexity of
earlier than this, actually. Earlier, I believe. Yes, right around here, right? So, okay. I suppose I should ask a clarifying question. What is the time complexity that is required under the statistical approach to model checking here? So is it exponential in the state size, or is it polynomial in the state size, or?
So there are two approaches in which one is numerical approaches. They are exponential. In the numerical approach side, their complexity is exponential to the state space size, And the statistical approach side, their complexity is quadratic to the desired accuracy.
Okay, thank you for the answer. I might want to follow up with you after, but thank you.
Thank you.
Very nice talk. So you say your algorithm is quadratically faster than the classical one. What size of problem instance do you need for the quantum approach to be faster than the classical approach?
Actually, so you mean what size of problem can be accelerated in practice?
So I imagine that for small problem instances, the classical approach is still faster just because classical computers are very fast. But then at some point, this quadratic complexity will kick in. And I wonder, this quadratic improvement of the complexity will kick in. And I wonder, what's the size of the problem for which the quantum computer will be faster than the classical computer?
Actually, you don't have specific idea because it depends on the cost of single quantum gate. Because even if you have this asymptotic advantage that quadratically speed up over the same accuracy, but in practice we need to consider the single quantum gate, the cost of single quantum gate.
You can look that up in the manual.
Yeah, but I think that is depends on the quantum hardware. So.
Okay, that's fine.
Yeah,
thank you.
Yeah.
I would like to ask were there any interesting problems when applying quantum amplitude estimation to your algorithm? Because you also keep around all the previous states, not just the final one, I think. Right?
Could you speak again?
While running the transition system, you keep around not just the final state, but the previous ones as well. Did that have any effect on the quantum amplitude estimation algorithm? Did it work well? Did you need to fix anything?
No, you can use the general quantum amplitude estimation because we already encode we already encode the all result into the result qubit. So only thing we should do is just extracting the probability of the being true state in the result qubit. So you can extract this probability using just general quantum amplitude estimation.
Thank you.
Yeah.
Thank you. What, okay?
Yeah, thank you.